In our course, Linear Systems 2, we will be studying the so-called linear systems, okay, as the name indicates. In particular, we will be dealing with various properties of linear systems. Okay. Sometimes we will cover certain properties briefly, and sometimes for certain properties we will go deep. Okay, we will study them in detail. But roughly speaking, this course will be about 3 concepts, okay, associated to linear systems, and there are also 2 for more general cases, but we will be focusing on linear systems in this course, and those concepts are stability, controllability, and observability. Okay. So we all have a rough, or some of us precise, ideas on what those concepts were, but let's remember them once again through a visual example. Okay. So consider the following system. Namely, we have 3 tanks, and they're connected to one another, and also one of them is connected to a water supply, and that system can be called a liquid reservoir system, and let that liquid be water. Okay, so we have the following, let's say water reservoir system. Okay. Where rate of water flow through links, through pipes is proportional to the pressure, okay, to relative pressure. Okay, so what that explanation means is the following. Suppose that we have 3 tanks. Okay. Here we have first tank. We have second tank. And here we have, let's say, third tank, and they are connected to one another. Okay, and they store water. Okay, here we have some water. Here we have some amount of water. Here we have yet some water. Okay. So those things, they're not identical in the sense that they have different base areas, and let's call those areas, denote those areas by C's, okay, C1, C2, and C3, okay. And then this is how we denote the level of water inside, H1, H2, and here we have H3. Okay, suppose that the cross section is uniform, it's always the base area, hence it's very easy to compute the total amount or volume of water in any given tank. Okay, all you have to do is multiply base area by the height of water. Okay. And as for the pressure, it depends on, clearly, the difference between the heights. Okay. Now to each link, there is a positive constant, okay, associated, and that constant depends on how small or how big the cross section of that pipe is. Okay, it's not that important, but that's what it's determined by. And then, so this is our system, and to this system we have the following external input, okay, which we're calling U. From this pipe, okay, from this channel, we can pour some water into the system through the first tank. But this water can reach to other tanks because the tanks are connected to one another. Okay. So let's be precise about our labeling. C1, C2, C3. We said they are the areas of tanks. Okay, therefore their units, for instance, could be meters squared because we're talking about area. And then H1, H2, H3, the height of water in tanks. Okay, therefore we can measure them in, let's say, meters. What else? U is the rate of water inflow. Okay, so this is more precisely to the first tank. And we measure it, or we can measure it, let's say, by liters per hour or meter cube per second, or something similar. So this is our input for the control. And finally, suppose that we can measure somehow the total amount of, okay, perhaps that's what we're interested in, the total amount of water in the system, meaning that the volume of water here, plus water there. So total amount of water in the system. Okay, and this is our measurement associated with that system, which is usually called the output to the system. Okay, now suppose that we want to understand this system, we want to work with it, perhaps we want to predict its future. So what we need for all those purposes is we need an accurate enough mathematical model. Okay, so we can get numbers out of that system, something, some quantitative information. So let's obtain a model for the system. Okay. And usually modeling is quite a difficult, and sometimes it requires some intuition task, but for this system it's quite straightforward, so let's do it. What we have is, okay, let's introduce new variables, V1, V2, V3 as the volume of waters in first tank, second tank, and third tank respectively. So this is water volume in tanks. Okay. Now clearly this volume is directly proportional to the height because the areas are fixed. In other words, we have VI equals CI times HI. I is our index, either 1, 2, or 3. Okay, now let's write the differential equation to be satisfied by these amounts of water. Okay, so V1 dot, so rate of change of total amount of water in the first tank is V1 dot. Remember that this dot means time derivative with respect to time. Okay, so V1 dot equals what? So there are two things. Okay, first of all, if we didn't have this connection, okay, suppose it's not connected anywhere and there is no input here, V1 dot, V1 would stay constant for all times, therefore V1 dot would be 0. Okay. But there's some interference to that water in the first tank. One interference is through this input. Okay, if you feed water to the system, what's going to happen is the volume will increase. So that means when there's some water flowing into the tank 1, then we want that must be positive. Okay. What else? We have another way to modify the amount of water within tank 1, and it's through this connection. Okay. So the water can move from this tank to the second tank, or vice versa, from first to second tank to the first tank. The direction of that motion is determined by the relative pressure, or determined by the heights. If, for instance, H2 is larger than H1, then the pressure here is larger than the pressure here, so that means the water will be flowing to the left. If, as it's drawn, H1 is larger than H2, there will be more pressure here than here, and then the water will travel from tank 1 to tank 2. Okay? And how fast it travels is determined by this coefficient alpha 1, 2. So overall, V1 dot equals alpha 1, 2 times H2 minus H1. So we have alpha 1, 2 and alpha 2, 3, they're positive. Okay. So this term represents this connection here. Okay, so alpha 1, 2 is positive. Therefore, when H2 is larger than H1, the pressure here is larger, and then the water is traveling to the first tank, meaning that the volume is increasing. Therefore, V1 dot should be positive when H2 is larger than H1. In the other case, like it's drawn here, if H1 is larger than H2, then pressure is larger here, and water is escaping to the second tank, meaning that the time derivative of the volume must be negative. Okay, so if H1 is larger than H2, then this should be negative. Therefore, this is how you determine whether it's H2 minus H1 or H1 minus H2. So this term represents this connection, and we also have the input, the water coming from the input. It's meter per second, so we directly add it. Okay. So that's the differential equation describing the water volume in the first tank. Let's do the same thing for the remaining tanks. How about we do that? There are two things that affect the volume of water in the second tank. One of them is this connection, the other is this connection. So what we have is alpha 1, 2 times H2 minus H1 or H1 minus H2 plus alpha 2, 3 times the difference, H2 minus H3 or H3 minus H2. Now let's determine the sign. Remember that these constants are positive. Okay? So for this connection here, if H2 is larger, okay, let's say, okay, if H1 is larger, then the water is than H2, then water is going to the second tank, therefore V2 dot is increasing. So that means we have to have H1 minus H2. Okay. Therefore you take this term and just swap the sign. And likewise, for this guy here, we should have H3 minus H2. And finally, for V3 dot, we have alpha 2, 3. We have only one means of affecting the water level, and it's through this pipe that is connection to the second tank, and it's alpha 2, 3 times H2 minus H3. Okay? If H2 is larger than H3, then here we have more water. That means the water will be escaping to the third tank. Okay? Therefore, it should be positive, and H2, the V3, that must be positive when H2 is larger than H3. So that's our model. But let's make our model such that, put it into another form, such that we have both on the right side, left-hand side and right-hand side, the same variables. Okay. On the right-hand side, we have H as our variables. On the left-hand side, we have the volumes. But let's make all those variables uniform. And for that, we can easily use that relation between volume and height. Okay. So rewriting these equations by using the relation Vi equals Ci HI, which we apply immediately the I dot equals Ci Hi dot, because Ci is our constant. Now we can rewrite that set of equations. Okay. We can write therefore H1 dot equals, now V1 dot is C1 H1 dot, so we can replace this by C1 H1 dot, and then we can divide both sides with C1, and here we would have H1 dot equals this guy divided by C1, and also that guy divided by C1. In other words, we have minus alpha 1 2 over C1 H1 plus alpha 1 2 over C1 H2 plus 1 over C1 U. Okay, so that's our first state equation, and then we have H2 dot equals, this time replace this with C2 H2 dot, and then we divide both sides with C2, and then we have alpha 1 2 C2 H1 minus alpha 1 2 plus alpha 2 3 C2 H2 and plus alpha 2 3 C2 H3. Okay, so that's the second equation rewritten, and finally we have H3 dot, which equals alpha 2 3 C3 H2 minus alpha 2 3 C3 H3. Okay, now we have both on the left hand side and right hand side only the heights. That's nice, because that would allow us to put this thing into the so-called state space representation for our water reservoir system. Okay, so let X, H1, H2, H3. Now we collect all those variables, H1, H2, and H3, and make a vector. And that vector, from now on, will be called our state vector. Now, once we have a state vector, we can now easily write down or put this set of equations into the matrix form or state space form. Okay, so let X be the state vector. Okay, then we have the following linear system representation of the water reservoir system. Okay, here we have H1 dot, H2 dot, H3 dot, that is, here we have X dot. So X dot equals, for each term we have a linear combination of the state variables and input. Therefore, we can collect all those coefficients, okay, in the matrix, and we can write X that equals something times X plus something times our input U. Okay, and entries of those matrices, this will be a 3x3 matrix because the state is in R3, okay, and this will be a 3x1 matrix or columnator because we have a single input. Okay, so what are entries? So for the first row, we'll look at the first equation, H1 dot equation, because it's our first state variable. What we have is minus alpha 1 2 over C1, alpha 1 2 over C1 for H2. We have plus 0 times H3 and plus 1 over C1 times U. So that's the first row coming from the first equation. For the second row, we look at the second equation. Here we have alpha 1, 2 over C2. For H1, we have minus alpha 1, 2 plus alpha 2, 3 over C2 for H2. And for H3, we have this alpha 2, 3 over C2. Okay, plus 0 times U, so that means this entry must be 0. Okay, and finally, for the third row, we look at the third equation. 0, alpha 2, 3 over C3 minus alpha 2, 3 over C3, and no input appears in the equation. So this is our model put in state space form. Remember that we also had a measurement which we call output. Let's also make it part of this model because it's something important associated to our system, associated to how we look at the system. So y equals what? Okay, now the output or the measurement was the total amount of water, and this is namely, output is V1 plus V2 plus V3. We no longer have V's, but we have H's. So we have to express that summation in terms of H's, and that's very easy. C1 times H1 plus C2 times H2 plus C3 times H3 is what we're talking about, the total amount of water in the system. So, this matrix almost always will be denoted by capital A. That's our system matrix. This is our input matrix, okay, B, and this is our output matrix, which is usually denoted by C. When output depends on the input also, we will have D term here, okay. It's Cx plus D times Q, but in this case, the output does not directly depend on the inputs, therefore we don't have a D matrix, or you can say we have a D matrix, but it's okay. So, in short, we have x that equals Ax plus Bu and y equals Cx. This is a linear system expressed in state space form. There are many other ways to express a system or linear system, but this is both for theoretical and practical point of view. That's the most beneficial way, it turns out, to represent, to express a linear system. Okay. So this is a linear system in state space form. Now, let's suppose that we're interested in certain problems associated to our system, okay? And we will put forward those problems through some simple questions. Suppose that we're interested in the answers to the following questions. Q1, question 1. Suppose that input U is constant. Okay. Now what will happen to the output in that case? Will the output y of t stay bound? Okay. Now, that's a question which is related to the behavior, the relationship between the input and the output. If the input is well behaved, in that case, when the input is well behaved, the output will also be well behaved in a certain sense. And questions like that will be studied under the title stability in this course. Okay. Another question that might be of interest is the following. Suppose that initially, let's say on Monday, H1 equals 5 meters, H2 equals 10 meters, and H3 equals 5 meters. Okay, that's the amount of the water levels in our tanks. Can we find an input function u of t, assuming that we have control over our input, so that H1 equals 10 meters, H2 equals 5 meters, and H3 equals 20 meters. Okay, so we start from some initial configuration, and then we want to reach to a final desired configuration for some reason, and we want to do that. And the only way that we can do it, that is through controlling this input, because that's the only way that we can interfere with this system. So therefore, it's an important question. Can we choose our input, control input, in such a way that, starting from some initial condition, we can, after some time, let's say an hour later, we reach to some other configuration. And questions of this sort are related to so-called controllability, which will be another thing that we will study in this course. And consider our last question, for example, Q3. Suppose that ut is known, which is reasonably assumed because ut is our control input. We are applying the input, therefore it's reasonable that we know what we're doing is known. And y of t, our output, the measurement, is measured and recorded. Okay, is measured for a week. Okay. Now, the question is, can we determine H1, H2, H3. So we don't have, let's say, a direct way of looking at the tanks. They're, let's say, buried underground or something like that. But we can somehow figure out the total amount of water, and we measure it. We also know what input we apply. The question is, can we figure out each of these heights, individually H1, H2, and H3, at the very beginning of the week, let's say on Monday, at the beginning of the week. Okay. And the concept that's very closely related to questions of this sort, namely, you look at the output, you look at the input, look at the input, you look at the output, but you don't have means to look directly inside what's going on, okay, to the internal guts of the system. But there are many situations in which you want to be able to figure out, you want to know what's going on inside, you want to know the details regarding the system, and then in that case, the questions of this sort becomes very important. While looking at u and y only, can you determine the state, okay, x. And that's what we will study under observability. Okay. So let's therefore write down explicitly the main message of this introduction lecture, which is that in this course we will be studying also some other stuff, but basically we will be concentrating on those three things: stability, controllability, and observability. Okay, so in course we will mainly be interested in three things: stability, controllability, and observability. Okay. And of linear systems. Now, these concepts, clearly, they're not peculiar to, they're not special to linear systems only. They're general. They're important for general case for non-linear systems. But they're understood best for linear systems. The tools that have been developed to study such concepts is very advanced for linear systems. For non-linear systems, there are still many unsolved issues. Okay, so following is what we call a linear system. In continuous time. Continuous time linear system. So x dot equals some matrix which may have time varying entries. In our example, all the entries were constant. Times xt plus dt times dt, and y of t equals ct times xt plus dt times u. Okay? And in our example, the D matrix was 0. Okay, so this is called a continuous time linear system. U of t, where we have a t is a square matrix n by n, and this number n is called the order of the system. Okay. And E matrix for each time it's an n by something matrix, and that's something, let's call it k. And k would be the number of individual input signals that you have in the system. In our case, we had just one input, which was the water coming from the pipe. Therefore, k was 1. And C of t for each time is something by n matrix, and again in our case we had a scalar output, therefore that something was 1, it was a 1 by n matrix. And d of t has to do with how many individual inputs and how many individual outputs you have. So it would be an n by k matrix, and the number of individual outputs, and k number of individual inputs you have for all t greater than or equal to 0. Okay, unless otherwise stated, we will always take the initial time starting point to be 0. Okay, and then these signals x, y, and u We know what they're called, but for the sake of completeness, let's write them down. The signals are called. Okay, so x will be function of time, and it's, each time it's a vector in Rn, and this is what we call our state. Okay, state of our system. U R K is the input of our system, and Y is function to R M is measurement, or sometimes called the R. Okay. Now, this is the continuous time linear system. We will also talk about, from time to time, the discrete time version, in which case this x dot becomes the value of the state at next time instant. And by time instant, we mean discrete time starting from 0 and taking integer values 0, 1, 2, 3, and so on. Okay, so let's also put that representation down. So this is what we call a discrete time system. Okay, x t plus 1, the value of the state at next time instant, equals a t xt plus et ut, and y of t is ct xt plus dt ut. Okay, to differentiate between continuous time and discrete time, usually the discrete time variable is denoted by a k, but we're following the book's notation, and the book's notation, both continuous time and discrete time are denoted by the same letter, t. Okay, where this time we have, since we're talking about discrete time system, t is 0, 1, 2. Okay. So it takes integer values only. And compact notation for a discrete time system, which is not universal, but it's now quite widely accepted, is this x plus equals a tx plus b tu, and y equals ctx plus dtu. Okay. So that here means derivative with respect to time, and x plus here in discrete time means it's just, in a sense, a propagator operator. So this means the value of the state at the next time instant. Okay, then just a few more details. Okay, so once again, by a linear system, we mean either this continuous time system, which is the usual representation that people use, but keep in mind that there are many other ways to represent a linear system. Okay, but we're going to stick to state space representation. This is the continuous time linear system, and this is the discrete time linear system. These are the objects, okay, the entities that we will be studying in this course. Whenever the matrices that appear in our representation, namely ABC, and dt. Suppose that they're all constants, okay, like was the case in our example with water tanks. Then the system is called linear time variant, okay? And in short, we're going to call it LTI. That's an LTI system when the matrices are constant. For constant matrices, it's a continuous time LTI system, and for constant matrices, this is a discrete time LTI system. The general case where the matrices are allowed to be time varying is called the linear time varying case. Time dependent is called linear time varying case. LTV is our abbreviation for it. Clearly, LTI system is a special case for the LTV representation, or LTV is a generalization of LTI. Okay. Now, before we end this introductory lecture, let's very quickly remember the two basic properties of linear systems, and then we can end this lecture. Okay. One nice thing about linear system is that it allows us a very special thing that we cannot do for nonlinear systems, and that special thing is called superposition. So that will be our first property that I want to emphasize. Properties of linear systems. Okay. So let's consider. Suppose that we're representing our linear system with this box. It's an nth order linear system where we have the input represented as an arrow entering the box, and we have the output. Okay. Now, output depends on the input, but it does not depend only on the input, okay, because it's a dynamic system. The relation between input and output is not algebraic. Okay. We also have to take the initial condition into consideration. Okay, so initial condition x equals x1, x2, xn. Suppose that this vector x is a shorthand notation for the value of the state at initial time. Let's call initial time 0. Okay, so this is the value of the this is the initial condition vector. For instance, if you have a circuit, a dynamic circuit, this contains the initial capacitor voltages and initial inductor currents. If you have a mechanical system, this represents the initial positions and initial velocities of certain links, let's say, of a robot arm. Okay, so note that, which is obvious, but it's important to emphasize, note that output depends on three things. Okay. Namely, because it's changing with respect to time. The input, okay, input signal, and let's show that. Remember, it's time varying. So input signal and initial condition vector. So by keeping that in mind, or motivated by that, let us write y as this is a function of t, time. It's a function of x or x0, which is the initial condition, and also u, okay, which is a function of time. Okay. For all future times. Once again, we take initial time to be t equals 0. So this is time, this is initial condition at initial time t equals 0, and this is our input. Okay. Now, first property, as we said, that we want to emphasize is property of superposition. So, property 1. Linearity of the system allows us to do what we call superposition. What we mean by that is the ability to write the following. We can write y of t, alpha x plus beta z, gamma u plus delta v. Okay. This equals what can be written as the sum of the following things: alpha y t x 0 plus beta y t z 0 plus gamma y t 0 u finally plus delta y t 0 b. Okay. Now it's easy to write, but it's important that we interpret this equation correctly. So this means the following. Suppose that we have a system, okay, let's say a second order circuit with a capacitor and inductor. So X would, initial condition would indicate the initial inductor current and initial capacitor voltage. So you perform 4 experiments with that setup, okay? In the first experiment, you set the initial condition to something, let's say 6 amps for the inductor current and 2 volts for the capacitor voltage. You apply no input, you kill all the sources, and then you run this. You obtain an output, let's say some resistor voltage, and you record that. And then you set everything to 0 once again, and this time you set the initial condition vector to something else, okay? Some other initial capacitor voltage, some other initial inductor current. Again, inputs are 0, start the system, measure the output, okay? So that's your second experiment. And in the third experiment, this time you set all initial conditions to 0. 0 capacitor voltage, 0 inductor current, no initial stored energies in our dynamic components, and you pick some signal, okay, input, let's say some sinusoid, and then you record the output. And in the fourth experiment, you do the same thing with a different input, okay. And then in the fifth experiment, you choose an initial condition that's a mixture of initial condition here and initial condition here, a linear combination. And you choose the input that's a mixture of the input in the third experiment and in the input in the fourth experiment. And then it turns out that if this is the case, you don't have to run that fifth experiment. Suppose that running experiments is expensive. You can directly compute the expected output by simply superposing in this manner the results of the previous experiments. Okay? And this property is called property of superposition, which is not true for general nonlinear systems. The other property is something that we're very familiar with from our everyday life, okay, which is causality. Okay, so suppose I've given two inputs, input signals. One of them is called U, the other is U hat, satisfying ut equals U hat t. Okay, they're the same input, not forever, but for a while. Okay, for the first, let's say, half minute, okay, or for the first day, for O 0 t and capital T. Okay. Okay, so you have U, let's say, U of t, t 0. This is t, and until capital T, U hat is exactly the same as U. Okay, but from that point on, it follows a different path. Then, until this time, supposing that we start from the same initial condition, outputs for these two different inputs will be the same. Okay. Then y t x u equals y t x u hat for all times between 0 and capital T. In other words, present depends only on the past and not the future. That's something that we inherently feel in our everyday lives. The present value of the solution depends only past values of the input. And clearly not on its future values. Okay, so those properties are what we wanted to emphasize regarding the linear system.